The last part of this series of lectures, and today we'll talk about algorithms. We'll talk about augmented Lagrangian methods in the first part, and in the second part we'll talk about inexact restoration methods. We won't have time to cover duality, but there are some informations in the slides here. You can check that later. The idea of the augmented Lagrangian method is to improve on the external penalty method. So just to remind you what we have shown about the external penalty method, we had this sequence of parameters ho k that goes to infinity, and for each k you have to solve this easy constraint subproblem. Okay, you choose some constraints that you think you are able to deal with them, and the other ones you penalize on the objective function. And we showed these two results. If this sequence is well defined, then every limit point is a global solution to the problem to minimize infeasibility, to minimize this infeasibility measure. And if the limit point is feasible, then if there is a feasible point, then every limit point will be a global solution to the problem. Okay, so for this to happen, remember you have to ask for global solution at each subproblem, and this is hard. And you have to actually make this sequence tends to infinity, otherwise you won't reach the solution. So this is a problem in practice. So that's why this method is of little practical relevance. If ho k goes to infinity, these subproblems are very hard to solve because of ill conditioning, and finding global solutions is almost impossible. So what we can do in practice, we can only find approximate stationary points, okay, even for unconstrained problems. In this lecture, I will assume that the subproblems are unconstrained. Okay, so we penalize with respect to every constraint, and we want to develop some strategy to keep this parameter ho k bounded. Okay, so we'll try to do this. And one idea to do this is to change the penalty function. So we have used this function, the squared L2 norm penalty. It's a nice differentiable function, but we could change this for this other L infinity norm penalty. If we do this, we have this result called the exact penalty result. If ho is sufficiently large, so there exists some ho bar such that for every ho greater than this ho bar, when you solve this subproblem with this other penalty function, you get the global solution to the original problem. So in fact, with this penalization, with this penalty function, you don't have to increase the penalty function to infinity. The difficulty here is that this function is non-differentiable. Okay, so there's a maximum and an absolute value. So there are some points here where you can't differentiate this function. And it's particularly difficult because these are exactly the feasible points of the problem. So if you want to deal with this kind of subproblem, you should be able to solve a non-constrained problem with non-differentiable objective function. So this is not what we want to do. You can do this, of course. There are some techniques to do this, but our approach is to take advantage of the differentiability of this function, so that at each subproblem we can solve them with continuous or smooth techniques as the Newton method or something like that. And so to develop this idea, let's consider only the equality constraint case. So just to fix ideas. And let me show you this sufficient condition for optimality, and this proof will give some interesting insights about the Augmented Lagrangian method. So let's assume that x star is a feasible point for this problem, such that there exist Lagrange multipliers associated to this point. So it's a first order stationary point, and we will assume also that this condition holds. It's called the second order sufficient condition. So this says that the Hessian of the Lagrangian function, this should be squared here. So the Hessian of the Lagrangian function for this, the correct multiplier, should be positive definite on this space. On this subspace, the subspace of directions orthogonal to every gradient at x star. So what we can prove is, in this case, x star must be a solution. So it's the sufficient condition. In fact, using the technique that we employed to prove the KKT conditions, we can prove the second order necessary condition. That is, it's very similar to this one, but instead of asking positive definite, you ask for positive semi-definite. So this is greater than or equal to 0 in this subspace also. So we could compute, as we computed first derivatives when we were developing KKT conditions, we can compute second derivatives, and this goes well. Okay, so let's try to prove this, the sufficient condition. And the idea here is to consider this other problem. Okay, it's an equivalent problem. Note that we penalize the function, the constraints, but we still add here, we keep the constraint. Okay, so note here that this other problem is equivalent to the first one. Okay, for every feasible point, the objective functions are the same. This term that I added here, I do not add anything if I am at a feasible point. So the solution should be the same. You can use this problem to solve the first one. But note that the behavior of an algorithm when applied to this method should be different. Okay, because at least if you use a method such as the external penalty method that walks through infeasible points, the objective functions will be different and the sequence generated are not the same. Okay, but let's consider this problem. And let's consider the Lagrangian function for this auxiliary problem. So this is what is called the Augmented Lagrangian function. It's simply the usual Lagrangian for this augmented problem. So here it is. Here it's the objective function, f, plus the penalty term, plus the term with the Lagrangian multipliers associated to the constraints. Okay, this is a classical way to define the Augmented Lagrangian. And for our purposes, sometimes it's easier to look at this function in this way. It's the same thing. If you open these squares here, you get exactly a term like this, plus some constant terms, and it's the same. You can think of this as, instead of applying the external penalty method where you penalize the constraint h of x, you penalized displaced violation of the constraint. Okay, you're not penalized violation of the constraint, but a displacement given by this parameter. And it's intuitively correct to think that as whole tends to infinity, this displacement should be 0. You should penalize the constraint, not merely a displacement. But if you are not at infinity, maybe this works fine. And so what we will prove is that x star, this point that fulfills the second order sufficient condition, is a local minimizer to the Augmented Lagrangian function, if you take ρ large enough. Okay, you don't have to make whole goes to infinity, it's simply large enough, then this x star will be a local minimizer for this function. And to prove this, let's evaluate some derivatives. So remember, I have a Lagrange multiplier, lambda star, associated to this point, x star. So this is the augmented Lagrangian, and these are the derivatives when I evaluate it at this point, x star, lambda star. So it's a simple computation here. This is the derivative of this part, this is the derivative of this part, and this is a sum of squares of the constraints. The derivatives are something like this. And I can put these terms together, this, and I get something like this, okay? And so note that this is 0. Since x star is feasible, this terms goes to 0, and the remaining terms is simply the gradient, the Lagrangian condition. Okay, this lambda star is such that this term is 0. So this is 0. Okay, so we want to prove that this is x star is a minimizer. So we are close to that goal. The derivatives should be 0. And let's look at the Hessian. So the Hessian now, we are looking at this formula, and we want to compute its derivative with respect to x. So this gives you the Hessian. This gives you, if you compute here, you use here the product rule, you get here the Hessian term plus this term here. It's the derivative of this term plus this one times this one. So it's something like this. And this left part here is simply, this is 0 again. Age of x star is 0. This is feasible. So this is the Hessian of the Lagrangian, the usual Lagrangian. So it's something like this. And so what we get is that the Hessian of the augmented Lagrangian has this form. It's the Hessian of the usual Lagrangian plus this term. And what we will show that this matrix is positive definite if you take whole large enough. Okay, so this is what this lemma here shows. So I have two symmetric matrices, P and Q, and Q is positive semi-definite. So P will be the Hessian of the Lagrangian, and this will be Q, a positive semi-definite matrix. Both of them are symmetric matrices. And the second order sufficient condition says this, that the Hessian of the Lagrangian is positive semi-definite on this subspace, the subspace of direction. Note that if I take here Q as this matrix, I simply get that subspace that I'm assuming that the Hessian of the Lagrangian is positive definite on that subspace. And then under these conditions, we will show that this matrix, P plus whole Q, it's the Hessian of the augmented Lagrangian. This is positive definite when whole is large enough. So this is the proof. Let's assume that this is not the case. So no matter how large I take whole, this matrix will never be positive definite. So I can take whole in this form K. So I take increasing sequence of whole here. So take every natural number. And for each natural number k, I can find a vector xk such that if I multiply this at the left-hand side and at the right side, I get a non-negative vector. Okay, so this is saying that this matrix is not positive definite. So when I assume that, I have the existence of such vectors xk, and I can assume that this vector has a unit norm. Okay, so I can do this because if it's not the case, I simply divide here by the norm, and I get a normalized vector. I divide by the norm square, and I get a normalized vector with this same property. Okay, so now I have a bounded sequence, I will assume that it converges to some point x, at least in a subsequence, it converges to some point x. Okay, so this is, we can get a sequence with this property. So when I open up this calculation here, I get this, xk transpose pxk, plus k xk transpose q xk. This is less than or equal to 0. And since q is positive semi-definite, this should hold for xk. Now I'll simply take limits in this expression, and I will have this, x transpose qx should be 0. Note that if this was not the case, if this limit were positive, then when I take the limit at this expression, this would go to infinity. Be k times a positive limit, and k goes to infinity. This goes to infinity plus infinity, and this goes to some number. Okay, x transpose px. So this is a contradiction. This can't be non-negative. So this should hold. X transpose qx should be 0. So for x's with this property, non-zero x with this property, this should hold. X transpose px should be positive. Okay, so we have a contradiction. Since this inequality, this term is non-negative, so this inequality implies this one. So when I take the limit, it should be a non-negative number also. So it shouldn't be positive. So we have a contradiction. Okay, so this for sufficiently large whole, this matrix is positive semi-definite. So we have proved this. If our sufficient second order condition, this should be the Hessian of the Lagrangian. We have that this is positive for directions in this subspace, and so we can use lemma to assure that the Hessian of the Lagrangian is positive definite. Okay, so it's important here that when we compute the Hessian of the Lagrangian, we have this additional property. So under the sufficient second order condition, I had only positive definiteness on the subspace. But when I look at the Hessian of the augmented Lagrangian, I have positive definiteness in the whole space. Okay, so if whole is large enough. So this is precisely the sufficient second order condition for an unconstrained problem. If I have a problem to minimize any function f without any constraint, if the derivative is 0 at some point, and the Hessian is a positive definite matrix, I can assure you that this point is a local minimizer. Okay, you know that from first year calculus. And okay, so we have what we wanted to prove. X star is a local minimizer to the augmented Lagrangian function. If I know the correct vector of Lagrangian multipliers. This is the form of the augmented Lagrangian function. So this is saying that at x star, this is, if I compute the augmented Lagrangian at x star, this should be less or equal than the augmented Lagrangian on an x that it is in a neighborhood. But at x star, look what happens if I evaluate this function at x star. It returns the objective function, okay, because it's a feasible point. So age of x star is 0, so this returns the objective value f. And if now I'm looking in this neighborhood of x star, but if I'm looking only at feasible points, this remains true. The augmented Lagrangian evaluated at a feasible point return f. So I have proven that x star is a local minimizer for the constrained problem. Okay? This condition says that f of x star is less than f of x if I'm looking only at feasible points. So this is the definition of a local minimum. Okay, so this proves the sufficient second-order condition for the equality constraint case. And this proof suggests that minimizing the augmented Lagrangian is a good idea. Okay, so at least if this sufficient condition holds, the solution will be the unconstrained minimizer of the augmented Lagrangian if I take ρ large enough. So the idea of the method is precisely this. We increase the penalty parameter and minimize the augmented Lagrangian. And let's look at an example here. But the problem is that we should, this works if I plug in at the Lagrangian function the correct multipliers. I don't know the correct multipliers at this solution. Okay, so but let's look at what happens here in an example. I have this problem, minimize half of x1 squared plus x2 squared, and one simple constraint, x1 equal to 1. The solution is clearly 1, 0, and at the solution I can compute the Lagrangian multipliers. It's this vector it's this number minus 1. So, but let me look at the augmented Lagrangian function at any point x lambda. So it's the objective function plus the term here with the Lagrangian multiplier and the constraint plus the penalization term. Okay, and let's solve this problem. For a fixed lambda, let's minimize this augmented Lagrangian, and we can do this by looking at the gradient. So the gradient of this function is this one, and I will solve this equals to 0 to find a stationary point. It turns out that there is only one stationary point, it's this one. And this is the minimizer of this augmented Lagrangian. So see what happens here. If I if I take the true Lagrangian multiplier, it's minus 1, I get the solution no matter what's the value of ρ. Okay, this returns 1 if lambda is minus 1, the true Lagrangian multiplier. Okay, but if I don't know the correct Lagrangian multiplier lambda star, but if I'm able to build an approximation to it, in fact, I will have an approximation to x star. And I won't need to make ρ goes to infinity. Okay, so if this lambda is close to minus 1, no matter what's the value of ρ, this is close to 1. It's the correct value of the solution. So this seems to be a good idea to control the growth of this penalty parameter. If we have inequality constraints, this is what we can do. We have a problem of minimize f subject to inequalities, and we can add here, I can transform this inequality constraint in an equality constraint in this sense. I simply add these squared slack variables, so this is always a non-negative value. If this is 0, this is equivalent to saying that g of x is less than or equal to 0. Okay, so this is something that you can do to transform inequalities to equality, but that's more of a theoretical tool. If you do this in practice, you are adding this constraint of this form z squared, and these are never good constraints because they change rank in a neighborhood, at least in 0. When this constraint is active, this z should be 0, and in the neighborhood it changes from 0 to 1, the rank increases. So you lose regularity of the problem if you do something like this. So it's never good in practice. In practice, maybe you should ask for non-negative slack variable. You add here gi of x plus some z, equals to 0, and z is greater or equal to 0. This is something that you can do in practice, and you won't lose regularity of the problem. But for this theoretical analysis, you can do this, and let's look at what's the augmented Lagrangian for this function here. So the augmented Lagrangian subproblem is to minimize this function, and this function is given by this formula. It's h plus this displacement. I'm using here that equivalent description of the augmented Lagrangian, using this displacement, this penalized displacement. And so here now z is a variable for me. X and z are parts of a variable for the original problem, but it turns out that I can solve this for z. Okay, I can get rid of this variable z when I'm minimizing this augmented Lagrangian function. I can easily compute the solution. Note that if this term is positive, is non-negative, g of x plus mu over rho, if this is non-negative, if you take a z, a positive z, you will get a greater value here at this square, this term here. It's a positive term plus a positive term. You get squared everything. Okay, this will be larger than if I take this 0. So the solution should be that this z is 0 when this holds. Okay, so I can simply, if I know that this happens, I change z to 0. Otherwise, if this is negative, I can plug in some value of z here, such that this term is 0. It's the least possible value that this function assumes. Since I'm squaring everything, the least possible value is when this is 0. So when this term is negative, I can choose such z. Okay, so this is the optimal value of z. So I can rewrite the augmented Lagrangian function in this way. If this term is positive, z should be 0, so the correct term to add here is precisely this. Otherwise, if this is negative, what I should plug in here is 0. Okay, so I have this formula here. And so this is the correct term for the augmented Lagrangian. If you have inequalities, you could redo everything that we did before using this augmented Lagrangian function, but you can use this trick and it's the same. So this is the idea of the method. Given a penalty parameter rho k, I should be able to find approximations lambda k and mu k to the true Lagrange multipliers at the solution. And we find here an xk, minimizing the augmented Lagrangian when I plug in here the approximations of the Lagrangians that I have. So this is, I'm using here the penalty parameter rho k and the approximation lambda k mu k, and I want to find x minimizing this function. So this is the function combining equality and inequality constraints. You have f plus this this displaced penalty term, and this is the displacement penalty term for inequalities. So this is the augmented Lagrangian function in the general case. Remember that we had an additional constant term here, but since I'm minimizing this function, I don't care if I minimize with this constant term or not. The solution will be the same, so we can think that this function is the augmented Lagrangian function. Okay, so xk will be given as the minimizer of this function, and in particular, the gradient of this function should be 0 at xk. And when we compute these derivatives, we get something like this. Okay, so note that this is saying that xk is a KKT point, okay? But I used the wrong multipliers. If instead of lambda k, if I've used this one, and instead of mu k, if I have used this one, I would have a KKT point. At least the Lagrange condition would hold for this other Lagrange multiplier. Okay, so, but I only know now this Lagrange multiplier because I know xk. I wouldn't be able to know this value before solving this problem for xk. Okay, so what we can do now is to use this as your new approximation for the Lagrange multiplier. You can't use on the previous iteration, but you use this value for the next iteration. So this is how we update the Lagrange multipliers in each iteration. So lambda k plus 1 is given by this formula, and mu k plus 1 is given by this formula. Note that this is always non-negative. Okay, it's the maximum of 0 and something, so it's non-negative. And okay, so when we are solving this this subproblem, we don't need to worry about the Lagrangian condition. It always holds. What we need to worry is about the feasibility of this sequence. So xk should be approximately feasible, and I need to worry about complementarity. Here I don't know if complementarity holds. I'm adding here every inequality constraint, and so I should see if complementarity is being satisfied. But note that eventually it will hold. If xk is convergent to some point x star, and if I'm looking at inactive inequality constraint, the associated multiplier should be 0. Okay, I shouldn't be considering an inactive constraint. And this happens with this formula. If this gj of x star is negative, so if xk is sufficiently close to x star, this will also be negative. And when I take Ho k large enough, this negative value will be greater in sign, greater in value than this positive value. Okay, so this will be a negative value, as long as I take this to be bounded. If this is bounded, this is going to minus infinity, so this is negative, and this maximum returns 0. Okay, so the approximation eventually gets 0 for inactive constraint, and the complementarity should hold. So it appears that I'm converging to the solution, or at least the KKT point of the original problem.
Would it make sense to define lambda k plus 1 using rho k plus 1 instead of rho k, anticipating the effect that the change in rho would have, or not?
I didn't get it.
When you define lambda k plus 1...
Lambda k plus 1, I used Ho k.
Yes, would it make sense to use rho k plus 1?
It's not the correct estimator. Okay, the correct way to predict this is by using this formula. I get this formula. Xk fulfills this condition. So if I take exactly this Ho k, the Lagrange condition holds. Okay, so that's why I use this. But
yes, I understand that. But then in the next iteration, I will solve a problem which will have rho k plus 1 instead of rho k to start with. So I don't know whether it would make sense or not. Maybe for the analytical results, it's easier with rho k, but I don't know whether it would be just a mistake or just might make some sense.
I think it doesn't matter in the end, but I don't see why you should use Ho k plus 1 here if this is saying that the correct estimator is this one. I don't know.
Yes, but this is the correct estimator for the current function.
Yes, but I don't know if the next function, if OK plus 1 will be the correct estimator. Because the point will change. It will be xk plus 1. And
yes, no, I understand that the point changed, but if I think that the points will be somehow converging and I can anticipate that I would have a different row k, I don't know whether I could get maybe faster convergence with the...
Yeah, I don't know.
Maybe I'm wrong, but is that row k is not something that you are computing, it's something that you select. And so putting row k plus 1, it doesn't make too much sense, maybe, because in the next iteration, maybe you can put there row k plus 1 very large, and you cannot know it in advance. So, yeah, my opinion is row k.
Yeah.
Okay, I will talk to you about this later.
Okay. The idea, another idea of this method is, since we are using Lagrangian multipliers, the sub-problems change if I change the Lagrangian multipliers. Previously, in the external penalty method, I only get a different solution if I change ρ k. If I didn't change ρ k, the problem remains the same. But now the sub-problem depends on ρ k and depends on lambda k and mu k. So I can solve one sub-problem and I can check, well, everything is going very well. So I have a new approximation for my Lagrangian multipliers, and maybe I can plug these new approximations to the sub-problem, and I can keep the same value of ρ k. So if everything is going well, I update only the Lagrangian multipliers, and maybe I don't need to increase the penalty function. So remember that the idea is that I don't want to take this penalty function too large. Okay, so if a good iteration is performed, we can avoid increasing the penalty parameter. So what's a good iteration? A good iteration is an iteration that sufficiently decreases the infeasibility and the complementarity. So I must have a way to measure how the infeasibility is being reduced and how this complementarity is being reduced. So one way to do this, the infeasibility, we can check the norm of age, if this is small, and we can check this value. Okay, if I compute this value, Vk, for every constraint j, I can see that this is returns 0. This is a non-negative value. And this is 0 if and only if the point is feasible with respect to inequality and complementarity holds with respect to this point. Okay, it's a simple calculation. You see what you get if this is 0, and you will see that this should hold. Okay, so this is how we measure inequality, infeasibility, and complementarity. So if this measure is significantly reduced from one iteration to the other, and also the equality constraints are reduced, you simply don't increase the penalty function, the penalty parameter. So this is the complete algorithm. So you start with an initial approximation for your solution, initial approximation for your Lagrangian multipliers. You should always keep non-negative multipliers for inequalities, an initial penalty parameter, and you fix here some parameters sigma and gamma. And so you find xk, a solution to this problem, minimize the Lagrangian using these parameters. You compute now this measure of infeasibility and complementarity, and you check if at this iteration, this measure of infeasibility and complementarity, including the equality constraint, if this is reduced by a factor that you previously chosen. So you compare this with the value of the previous iteration. If this is reduced by this fraction, maybe 90%, you can keep the penalty parameter the same. Otherwise, so the iterations are not going well, you increase the penalty parameter by multiplying by this fixed parameter gamma. Okay, so and when you choose, this is to choose whole, the penalty parameter, and this is how you update lambda. You use this formula, and here we have to safeguard this parameter to keep them bounded. So I project this on a box, lambda min, lambda max, to keep this sequence bounded, such that our convergence theory will work. And we do the same thing to the multipliers associated to inequalities. Okay, you project in on this box, this positive box. Quer dizer alguma coisa?
Yeah. So, in practice, how would you do to get these boxes? Would it be easy to get some estimates, well, some values for lambda max and mu max?
The theory says that if you take them large enough, no matter how large, it will work. So, but in practice, I'm not sure how we should fix these things.
Because I guess in practice I could have, if I take lambda max very large, I might have the problems of ill conditioning you were mentioning before, no, for the subproblems. If I end up having estimates that are very large, I might have problems to solve each iteration because of the ill conditioning of the problem.
But the condition of the problem is associated to whole k very large, not lambda. If lambda is larger, you don't get a problem with conditioning. No. And another important thing, so this is what in fact what it's implemented in the Algorithmic software, or maybe some small variation of this, with this additional trick here. So we can get rid of augmenting the penalty parameter getting too large. So, but here I assume that xk was a true solution for this problem. Should be a global minimizer, at least a local minimizer, for this to make sense, for this approximation to be good enough. But in practice, you can replace this the minimization problem by a stationary point. So this works fine as well. xk may be simply a stationary point for this problem. So it's the gradient of this objective function here should be 0. But in fact, you can be more, you could be less strict and ask for an approximate stationarity of this point. So if you compute, typically you will compute this solution xk using some algorithm for minimizing an unconstrained function. So and this algorithm must be an affordable algorithm, and it will not generate local minimizers. It will generate some approximate stationary point. It will measure the gradient of the objective function, and if this gradient is small enough, the method will stop. Okay, so this is what you can do. And if you can incorporate this in theory. So if at each iteration this is smaller than some epsilon k, then epsilon k, with epsilon k going to 0, you should be strict at each iteration. You should be more and more strict about this condition, but this works fine in practice also. And this is the theorem that we are able to prove. The limit points of a sequence generated by this algorithm will be a stationary point for the problem of minimizing the infeasibility measure. Okay, so you don't get a feasible point, of course, but you don't get a global minimizer of the infeasibility measure. You get a stationary point for this problem of minimizing infeasibility. And now, even if a feasible point exists, I talked about this yesterday, even if a feasible point exists, I won't be able to find this feasible point. Okay, but if the limit point is feasible, so if this minimizer of the infeasibility turns out, if this is a stationary point for this problem of minimizing the infeasibility, if this is, this turns out to be the global solution, turns out to be a feasible point, then you can prove that the limit point of this sequence generated by the algorithm is an approximate KKT point. Okay, so it's a good, it's a point that fulfills a good optimality condition, a first-order optimality condition, and this means that if you have a weak constraint qualification, the KKT condition will hold. And also you can prove something about the Lagrange multiplier sequence that you generated. If you have Mangasarian-Fromovitz constraint qualification, this sequence of multipliers will be bounded. It's not what it's written here. This sequence would be bounded, and every limit point of this sequence will be true Lagrange multipliers. Okay, you get true convergence only if you have a linear independence condition. And I will end this part with these two remarks. In the sub-problems, instead of requiring first-order stationarity, as I did here, I could require an approximate first-order stationarity. I could require a second-order stationarity for the sub-problem. I could stop this algorithm not only with the gradient closer to zero, but with the Hessian of the Lagrangian close to being a semi-definite matrix. And there are algorithms that returns points like this. And if I do this, I get convergence under a weak constraint qualification to a second-order stationary point. So I replace global minimization and the sub-problems. If I have global minimization and the sub-problems, I have a global solution in the end. If I have a first-order stationary point, I get a first-order stationary point of the constraint problem. And the same goes with if I have second-order. And we can prove that the penalty parameter, in fact, remains bounded, but we need some strong assumptions, such as the linear independence condition and the second-order sufficient condition. So if this is the case, you can prove that the penalty parameter is, in fact, bounded. In practice, there are some tricks that you can do. For instance, in the beginning of the iterations, you don't need to be too strict about this epsilon k. So this is something that is explored in the implementation. And there are some other variations here. You can replace this measure here. If you use some other measure here, you in fact get this result. The penalty parameter remains bounded under a weaker constraint qualification. So there are many variations of this method, and many papers published about this. And in fact, what the augmented what Augen-Kahn does, it keeps the bound constraints, so it never penalizes with respect to bound constraints. So you assume that your problem has bound constraint on every variable, and the sub-problems is a minimization on a bounded set, on a box. Okay, and so there is a well-established solver for minimizing continuous differentiable function on a box. So it uses an active set strategy, and this is what is used in the Augen-Kahn implementation. And it's important, it's good to have something like that, because your sequence will be always generated inside this box. So you are always generating a bounded sequence xk. So at least you will have some limit point, and this is important. Okay, so let's stop here, and we come back in 10 minutes.
Okay, so see you in 10 minutes.